So chapter 7 is linear programming, and we're going to continue learning about the process. And then in section 7.3, we're going to pull everything together and do entire linear programming problems. So in 7.1, we started building some of the skills we need of graphing lines, then graphing linear inequalities, and then systems of linear inequalities. So we're going to do a quick review of that and create some feasible regions and then talk more about why we're doing that. So recall that linear programming is a way for a business to make decisions about how to best use its resources. And limitations on things are incorporated into the math so that they can make an optimal decision. So we're going to look at word problems like if a chainsaw needs 4 hours of assembly and a wood chipper needs 6 hours, and you only have 48 hours of time available, so that's your limitation, and your profit on chainsaws is 150 and your profit on chippers is 220, then the question that linear programming can answer is how many of each should be assembled for maximum profit? So that's the kind of question that we'll look at in 7.3. So building up to that, we're going to do a quick review of 7.1 where we start with an inequality. We replace the inequality with an equals and graph that line. We make it dashed if it's a strict inequality, which actually doesn't come up in practice in linear programming. It's just a small algebraic detail. Decide which side to shade and clearly show me your reasoning of how you decided. Then shade the appropriate side, or as you'll see, when I'm doing it, I use arrows. Now I find that it's a little cleaner and clearer. Different colors can really help. Do this for each of those given inequalities in the system and find the region that's the overlap of all the shading. So remember, there's multiple ways to graph lines. My two favorites are if the line is in slope-intercept form. If it already looks like y equals mx plus b, then plot the intercept of 0, b and use the slope m to find another point on the line and then connect those dots. You can do all equations of lines that way. If you want to take lines that are given you in the general form and solve for y to turn it into slope-intercept form, you can do that. But a lot of the equations of lines in chapter 7 are in this general form and are pretty quick and easy to graph using the intercept method as long as a and b divide evenly into c. So let's look at an example. We're asked to graph the feasible region. So that means the overlap of all these graphed inequalities. What does that look like? So it really helps to organize work. So I'm going to label the first inequality number 1 and then come down here so you can see the work that's connected to that first inequality. So I have 2y minus x is greater than or equal to 5. Well, 2 doesn't divide evenly into 5, so the intercept method is not going to be a useful choice. So I'm going to solve for the y by adding x to both sides. I get 2y is greater than or equal to x plus 5. And I'm putting the x first because I know I'm going towards an equation of a line. Then divide both sides by 2 and get y is greater than or equal to 1/2 x plus 5/2. So recall in section 7.1 we graphed a similar graph where it had halves in it, and so it's going to be a lot easier to do the graph if you can accurately graph a 1/2. So I'm going to use a scale, label my x and y axes. I'm going to use a scale where 2 boxes is 1 unit, because then I can accurately graph 1/2. Each box is 1/2. So I'm going to do the same thing on the y direction. So I can see that my y-intercept is 5/2, so that's 2.5. So I'm going to go up to 2.5 and see how I can precisely plot it on the graph because of my scale. So then my slope is 1/2. So from the y-intercept, up 1 over 2, make a dot, up 1 over 2, make a dot, up 1 over 2. I make as many dots as will fit on the grid so that I get a nice straight line when I graph. And then you're going to use a ruler or a straight edge. And so this is line 1. And now I need to decide which side to shade. So you either need to test 0, 0, or you can use the above below method because you see y is greater than these points that are on the line. So you want y values that are above the line. So I'm going to use arrows rather than shading, especially on the tablet here. It gets really muddy if I try shading. Okay, so everything above that line is potentially part of the feasible region. Okay, so now let's look at equation number 2. So I'm going to come over here to the right, and I have y is less than or equal to 3 plus x. Well, if I just rewrite this as y is less than or equal to x plus 3, we can see that it is in slope-intercept form. So I would come up to my y-intercept of 3 and make a dot. And then my slope is 1 because I'm not seeing a multiplier here. If it's helpful, you can put a 1 there. So it's up 1 over 1, up 1 over 1, up 1 over 1 is the slope of this line. So then you're going to make your straight line. That's line 2. And then we have to make our shading decision. Well, you can see that y is less than these points that are on the line. So I want y values that are below the line. So those are going to be this way, downward. So now you're looking for where is the region that has both kinds of arrows, and the arrows are pointing into that region. So do you see that it's kind of a triangular region, but then the x is greater than or equal to 0 and y is greater than or equal to 0. So I'm in quadrant 1. So I need to be above the x-axis, and I need to be to the right of the y-axis. So that tells me the tip of the triangle is cut off and is not part of the feasible region. Okay, and then just to tell you where we're going to be looking at points that are at what are called the corners. So this is a corner point of this feasible region, and this other point here is also a corner point. Okay, so that's graph the feasible region. So then the next objective is to use the graph of the feasible region to find maximum and minimum values of something called an objective function. So an objective is something you're trying to accomplish, right? So there's all kinds of math involved that we don't have to worry about. We just get to have the result that it's already been proved that the maximum and minimum value of whatever objective function you're looking at will occur at those corner points that we were just looking at. So we're going to have to be able to use algebra to find those corner points. So recall that we reviewed solving a system of linear equations because that's how we find the point of intersection of two lines. And then we can use our visual graph to double check our algebra. Okay, so for the graph we just drew, we graphed the line 2y minus x equals 5, and the line y equals 3 plus x, and then the line x equals 0 and y equals 0. So if we were asked to find the points of intersection, you're being asked to find the solution to a system of equations. So when one of the equations is already given as solved for one of the letters, then I'm going to use the substitution method that says take the 3 plus x, substitute it in for the y, and have 2 times 3 plus x minus x equals 5. So then we're going to distribute our 2, get 6 plus 2x minus x equals 5. And then get the x's together on one side and move any numbers over to the other side by subtracting 6 from both sides, and then combine your like terms, and you're going to get x is negative 1. Then you have a formula here that says if you know what x is, you can find y. So y is going to be 3 plus x, which is negative 1, so 2. And then we write our answer as an ordered pair, negative 1, comma 2. So let's go back and look at our picture and see if that seems reasonable. Negative 1, comma 2 is where we'd expect to see those lines intersecting. Sure enough, visually we can see that, but you have to use algebra. The instructions will always say to use algebra. Okay, so that's the point of intersection of those two lines with the slants. So now let's talk about the corner points. This first corner point is the y-intercept of line 2. Right? That's why it's so helpful to label things. So it's the y-intercept of line 2. So we can look at the equation of line 2 and say the y-intercept of line 2 was 0, 3. So we know that's one of the corner points. And then this second corner point is the y-intercept of line 1. And we found that here when we rearranged into slope-intercept form. And so we have that the y-intercept of line 1 was 0, 5 halves. So these two are corner points. This third one is just a point of intersection, which your instructions just said find the points of intersection. So this 7.2 is still a lot of just practicing the mechanics that we need to be able to solve a linear programming problem. So the feasible region is a graphic representation. So that's a fancy way of saying it's a picture of all the possible operating scenarios. If there's some kind of a constraint on a variable, a limitation, a condition, a requirement, it gets written as an inequality. If you say, I need to have at least 5 round tables, and x is the number of round tables, this is how you write the number of round tables needs to be at least 5. So all of these inequalities together create the graph of the feasible region, and it could look something like this, just depends on the problem. And each of these points where two lines meet is called a corner point. And we're going to find those points because they're going to be the points of intersection of lines. So then we're going to be trying to optimize something. In business scenarios, it's either profit, revenue, or cost. If we're looking at cost, we want to minimize cost. If we're looking at revenue or profit, we want to maximize those. But the process for finding a maximum, finding a minimum is exactly the same. So you write an equation for the thing you're trying to optimize, and that is called the objective function. So in this section, the objective function is given to you. In the next section, you're going to have to read a word problem and put together an objective function from the words of what are you trying to maximize or minimize. So I'm going to pause here and make a second brief video with this example of doing the whole process of graphing the feasible region, finding the corner points, and then finding the maximum and minimum values of the objective function.